Hello everyone. This is the final presentation of the design and fabrication of microsystem class. We are team 4 in Liuke in Dong-Weon. In this presentation, we're gonna explain about strain sensor-based pressure sensor design and fabrication using semiconductor process. In using wireless system, we evaluate the sensor performance. A piezoresistive pressure sensor is a device that converts pressure into an electrical signal using a piezoresistive effect. So when pressure is applied, the diaphragm undergoes the deformation, which leads to a change in the electrical resistance of the strain sensor. So using this Wheatstone bridge circuit, we can detect these resistance change and convert them into a corresponding voltage output. For that, firstly, we design the mask. This is the final mask pattern that we design. The first one for the open window, and the second for the metal sensor, and the last is for backside pattern. Here we can see when we separate the electrode of each sensor, will be more convenient to check each sensor's quality. In order to decide the thickness, we analyze the relationship between diaphragm thickness and the strain. So here we choose 40 micron meters so that it causes big strain at the metal sensor part. We got the linear relationship between pressure and the output voltage as shown in this graph. So this is the silicon wafer that we use. We measured the layer thickness around 150 micrometer and took this as a reference to conduct the final silicon etching and control the membrane thickness and remove the fabrication process. After wafer cleaning, we use the furnace equipment to do the first oxidation process. We complete the wafer oxidation step using the parameter of 1000 degrees Celsius for 40 minutes to obtain an oxidizing layer approximately 300 nanometer thickness. Then the first process to make an open window pattern, including PR spin coating and soft baking, and UV exposure and post baking. And we develop the pattern and then rinse it. And then we do etching. So in order to control the thickness of the silicon wafer, the first step is BOE etching process to remove the silicon oxidation of the open window pattern. And then we did the TMH etching to remove the silicon and control the thickness of the silicon. So TMH etching rate is 0.5 micrometer per minute. So in our desired thickness was 40. So we set the etching time as 18 minutes, and finally we got the thickness of 40.557 micrometer. Next, we do the second oxidation process to make a 300 nanometer silicon dioxide layer. After that, we make a sensor pattern on the silicon wafer. So using this sputter machine to deposit the chromium sensor layer. Before deposition on the wafer, it is recommended to do the pre-sputter for the wire to remove the oxidizing layer of the metal target. So, and then after that, we use the argon ion to hit the metal target of the chromium, and the chromium ion will fall down onto the substrate and the film will be gross. Our desired thickness was 200 nanometer of chromium layer. This is the detailed process. First, we put the chromium here, and after deposition, using this film mask, and we conduct the photolithography following from spin coating and UV exposure and develop the pattern. Then we do the chromium etching process to make the sensor pattern. And after remove PR, we could get the final sensor pattern like as shown in this figure. And lastly, we did the backside etching. We put the pier on both sides and do the photolithography process for backside pattern for the diaphragm. So during this process, we need to coat pier on both sides of the wafer, and this will easily cause some undesirable contamination. So the cleaning of spin coater holder and any other substrate will be very important. So then we do the TMH etching for backside. Since etching rate was 0.45 micrometer per minute and then calculate the etching time as 70.5 hour, the rear silicon thickness will be 48 micrometers. So we discussed about it is difficult to fully achieve the uniform TMH etching. So it is recommended to remove the wafer halfway through etching and change the direction of the placement to improve the uniformity of the final result. So this is our final result of our fabrication process. Next, we design the zig to hold the sensor and give a pressure through this channel and assemble. Here, we apply the pressure using this setup and check the pressure with this one, the regulator. And when we apply the pressure from 550 to 300 kilopascal, we check the deformation of our sensor. And this result looks very nice. We can clearly see the step as shown in this figure, and we could see the deformation of using through our eye. So that means that we make a diaphragm very nice. So next part is about the wired and wireless system. So we firstly set up the simple Whiston bridge circuit just for the test. And when the R4 is manually changed, that there will be the voltage output differences. So this is the setup for the data measurement system using two Arduino. And so this Arduino get the signal from the circuit, and using this RF module, it can communicate with another RF module and get the data. And this Arduino can connect with PC and make some simple real-time floating code and get the data. So this is our real-time floating program. When we got the signal, we could get the data in wireless, and using this data, we can calculate the relationship. I also make a function to save the data to further analysis. So using our fabricate sensor, we applied 1 volt and give the power. At the first, we considered the XH711 amplifier, but the performance is bad. I mean, performance is not good enough, so we directly used the commercial amplifier to amplify the sensor signal. So the output amplified signal was analog voltage, so we got the signal using this wireless system. As here you can see, when we apply the pressure here on the sensor, the voltage goes up, and then smoothly goes to down. Like this way, we evaluate the sensor performance. We evaluate the sensitivity, hysteresis, linearity, repeatability, and accuracy. And in order to analyze, we apply the low-pass filter to remove the noise. So this is the result. And we got the data for 3 times. And we apply the pressure from 0, 50, 100, 150, 200, 250, and up to 300 kilopascal and back. This is, and as you can see, there is a small initial offset. First, we compare the theoretical value from FEM simulation result in the yellow graph. And blue mean the amplified voltage that we got from our sensor, and the real voltage is shown in the green line. So that means the absolute error was 0.024 volt and the RMSE about 0.029 volt. The real condition and the expected data have some big error due to first, the silicon thickness is bigger than our desired value, and the second is the sensor's real resistivity has distance to the reference metal chrominum's value. Second, we evaluate the sensitivity. So the average sensitivity was 1.4 millivolt per kilopascal. Third, we evaluate the linearity. For three cases, we calculate the average linearity, which is 6.77%. So in my opinion, this is a reasonable value. For the hysteresis, I use the definition to calculate, and there is the average hysteresis error of 23.3 millivolt, which is a little big. For the repeatability, we calculate the repeatability error at each pressure, and the average repeatability error was 9.8 millivolt. So conclude, this project focusing on design and fabrication and performance verification of piezoresistive pressure sensor. It includes detailed explanation of production process and numerical analysis of pressure diaphragm, mask design, and shell design. So through this hands-on experiment, we gained some significant insight and deepened our understanding of physical principle and the manufacture process involved in the MEMS technology. So although we encountered so many challenges along the way, the sensor's performance was less than the idea in the end, the experience was invaluable. So this challenge emphasized with the part we need to improve and provide us a deeper understanding for the complexity of MEMS fabrication. So this is very good chance to learn and experience the sensor fabrication and make us to think about the sensor performance. So thank you for giving a good chance in to experience, and I'd like to conclude this presentation. Thank you.